In simple harmonic motion, the position of an object moves back and forth over time in a smooth, wave-like pattern that can be described using sine or cosine functions. This graph shows how displacement changes as time progresses, with the cosine function starting at its highest point, representing maximum displacement, while the sine function begins at 0, representing the object's equilibrium position. Which function we use depends on where the object starts at time 0. So, if the object starts at the peak of its motion, we use cosine, and if it starts from the middle, we use sine. Both functions capture the regular, oscillating movement seen in many physical systems.
Velocity is the rate at which displacement changes over time. Here, displacement is given by a sine function, which represents how position varies. When measure the changing gradient, we get velocity, which follows a cosine function. This means velocity reaches its maximum value when displacement crosses the equilibrium point, where the position is 0 and the slope of the displacement graph is steepest. Conversely, velocity drops to 0 at the points where displacement reaches its maximum or minimum values, where the graph flattens out momentarily. This relationship shows how velocity and position are connected through differentiation, with velocity leading position by a quarter cycle in this oscillation.
Acceleration is the rate at which velocity changes over time, expressed as the derivative of velocity with respect to time. In simple harmonic motion, this relationship is captured in the equation A equals negative omega squared times x, where omega is the angular frequency and x is the displacement. The acceleration reaches its maximum value at the points where the displacement is at its peak, and these are also where the restoring force is strongest. When the object passes through the equilibrium position, the acceleration drops to 0, because the net force acting on it is 0 at that point. The graphs illustrate this clearly. The displacement oscillates between positive and negative amplitudes, while the acceleration graph follows a similar pattern but is inverted and scaled by omega squared. This shows how acceleration is directly tied to the position and how it changes as the object moves back and forth. Here we see how displacement, velocity, and acceleration relate to each other over time in a cycle. Velocity leads displacement by 90 degrees, which means the velocity reaches its peak before displacement does. Similarly, acceleration leads velocity by the same amount. Importantly, acceleration and displacement are in antiphase, so when acceleration is at a positive maximum, displacement is at a negative maximum, and vice versa. These phase differences help us understand how these quantities change in relation to each other throughout the motion.
Here, we have a summary of the key equations that describe displacement, velocity, and acceleration in simple harmonic motion. Displacement can be expressed as either a cosine or sine function, with the maximum amplitude represented by A. Velocity is the time derivative of displacement, showing a relationship with both amplitude and angular frequency, and its maximum value occurs when the particle passes through the equilibrium point. Acceleration, which is the derivative of velocity, involves the amplitude and the square of the angular frequency, and it reaches its maximum at the extreme points of motion. The defining equation of simple harmonic motion ties acceleration directly to displacement by showing that acceleration is proportional to displacement but in the opposite direction, with a factor of the negative square of angular frequency. This toolkit gives us a clear framework to analyze any SHM system in terms of how its position, speed, and acceleration change over time.